Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to talk about two-stage least square method in EViews, known as 2SLS. A fundamental assumption in regression analysis is that the right-hand side variables are uncorrelated with the disturbance term. So, for example, if I talk about this equation, our basic assumption is that x1 is not correlated with the error term. If this assumption is violated, both OLS, that is ordinary least square, and weighted least square are biased and inconsistent. There are a number of such situations where some of the right-hand side variables are correlated with disturbance. So x1 is correlated with the error term. There are endogenously determined variables on the right-hand side of the equation. Now, what's wrong with the basic OLS assumption? It is impossible to imagine any equation in which all the independent variables are independent of each other. The most important thing is any model of economics or management is simultaneous in nature. For example, supply and demand of chicken is simultaneous. The price of housing is affected by the level of the economic activity and the interest rates and other factors simultaneously. What is the nature of the simultaneous equation system? Let's try to understand. The basic question, what came first, the chicken or the egg? This question is impossible to answer satisfactorily because chickens and eggs are jointly determined. There is a two-way causal relationship between the variables. The more eggs you have, the more chickens you will get. But the more chickens you have, the more eggs you will get. More realistically, the economic world is full of kind of feedback effects and the dual causality that require the application of simultaneous equation models. Such topics are usually modeled by distinguishing between the variables that are simultaneously determined. Y's are called endogenous variable and those that are not. X are called exogenous variable. Consider these two equations. Y1t is equal to alpha 0, the intercept, plus alpha 1 y2t plus alpha 2 x1t plus alpha 3 x2t plus epsilon 1t. Y2t is equal to beta 0 plus beta 1 y1t plus beta 2 y3t plus beta 3 x2t plus epsilon 2t. If you observe carefully, y1 is repeated here in the second equation and y2 is also in. So here, the independent variable, which is y2t here, becomes a dependent. And similarly, y1t which is independent here, becomes dependent here. These behavioral equations are also called the structural equations. Structural equations characterize the underlying economic theory behind each endogenous variable by expressing it in terms of both endogenous and exogenous variables. Researchers must view them as an entire system in order to see the feedback loops involved. If we consider this as a loop, y1t, y2t, this is the whole mechanism which is working. So the y's are jointly determined. So a change in y1 will cause a change in y2. Sorry, a change in y1 will cause a change in y2. A change in y2 will again cause a change in y1. Contrast to this feedback, if you change only x1 here, the effect will be only seen on y1. So this is the basic reason we consider all this as exogenous variable. Basically, they are outside the system and y's are considered endogenous because they are inside the system. There is a system, mechanism, a loop which is working. So if epsilon 1 increases in a particular time period, I'm talking about the error term, y1 will also increase due to the equation 1. If y1 increases, y2 will also rise. But if y2 increases in equation 2, it also increases in equation 1, where it is an explanatory variable. Thus, an increase in error term of an equation causes an increase in explanatory variable in the same equation. If epsilon 1 increases, y1 increases, then y2 increases, violating the assumption of independence between the error terms and the explanatory variables. So no longer we are able to use normal OLS methods. So to overcome such scenario, we are using a reduced form equations. So an alternative way of expressing a simultaneous equation system is through the use of reduced form equations. Equations that express a particular endogenous variable solely in terms of an error terms and all the predetermined exogenous plus the lagged endogenous variable in the simultaneous system. Let's go back to the original equation. If now I make y1 only dependent on exogenous variable, similarly y2 only dependent on exogenous variable, this is the thing which I got is a reduced form equation. So now my y1t is equal to phi 0 plus phi 1 x1t plus pi 2 x2t plus pi 3 x33 v1t. Similarly, if I talk about y2t is equal to phi 4 plus pi 5 x1t plus pi 6 x2t plus pi 7 x3t plus v2t. If you carefully observe, there are no endogenous terms on right hand side. All exogenous terms are only considered. So the previous equation has now been reduced, and this is known as a reduced form equation, where the v's are the stochastic error terms that is randomly distributed, and normally it's having a normal distribution. And the phi's are called the reduced form coefficients because they are the coefficients of the predetermined values in the reduced form equations. Note that each equation considers only one endogenous variable is present, and that is in the form of dependent variable. You should not include any independent variable as endo in the equation, and that each equation has exactly the same set of predetermined variables. The reduced form coefficients such as pi 1 and pi 5 are known as the impact multipliers because they measure the impact on the endogenous variable of 1 unit increase in the value of the predetermined variable after allowing for the feedback effects from the entire simultaneous system. Now, we will have to qualify one variable as an instrumental variable. In the above regression, that a regression X is stochastic and that is correlated with the error term. Let me tell you one thing. Why we are going for simultaneous equation method is that X is correlated with the error term. And as it has violated the basic classical 3 assumption, that's the reason we are going for simultaneous equation model. Suppose a variable z is a candidate instrument for X. We have qualified this z, which is a representative variable for X. But we should have some properties in z. What are those properties? Let's see. The instrument relevance, that is, z must be correlated positively or negatively with the stochastic variable for which it acts as an instrument, variable x in the present case. The greater the extent of correlation between the two variables, the better is the instrument. Symbolically, covariance between the x and z should not be equal to 0. I'm talking about the correlation between x and z. There should be strong correlation, either positive or negative, between these two variables. On the same time, instrument exogeneity, z must not be correlated with the error term mu. There is a covariance z and mu should be equal to 0. I'm talking about this term. The relationship between z and the error terms should be equal to 0. Note a regression in its own right. That is, it does not belong in the original model. It should not be in the original model. If it does, the original model must be misspecified. To solve the simultaneous equation model, we are having some approaches. The two-stage least square, the limited information maximum likelihood, K-class estimation, generalized method of moments, and three-stage least square method. Before we run the two-stage least square in EViews, we will have to identify the model. And the identification problem is the equation is under-identified. If the structure of the equation is not unique or there is not a sufficient information to uniquely distinguish the equation, then the equation is under-identified. I'll give you a very simple example to this. If I say x plus y is equal to 8, I again repeat, x plus y is equal to 8. So and I ask you that determine the value of x and y, it is not possible to determine because we are having only one equation and two unknowns. So it's the same scenario here. We want to identify that will be able to get the solution set or not. Equation is identified. There are two cases in this which are desirable: exactly identified and over identified. If there is a sufficient information available to distinguish the equation, then it is called just identified or exactly identified equation. If there is more than sufficient information regarding the equation, then the equation is called over identified. Now, how we will identify this? Let's see. I'll give you a relevant example. For an equation to be identified, the total number of the variables excluded from it but included in other equations must be at least as greater as the number of equations of the system less 1. Remember this terminology. Let G is equal to total number of equations, that is total number of endogenous variable. K, number of total variables in the model, endogenous and predetermined. M, number of variables, endogenous and exogenous, included in a particular equation. I'll be giving the relevant examples. The equation which you have to satisfy is k minus m, that is an excluded variable. So be greater than or equal to total number of equations minus 1. Let us assume for the first equation that g is equal to 10, k is equal to 15, m is equal to 11. G is 10 equations are there, k is total number of the variables are 15. And in particular equation, total number of variables in the model there are, so in 10 equations there are total 15 variables, and in a particular equation only 11 are present. So recall the order condition, k minus m, so be greater than or equal to g minus 1. So if you consider this, 15 minus 11 is less than 10 minus 1, thus the order condition is not satisfied and the equation is under identified. So order condition is not satisfied and therefore we cannot go for establishing the rank condition, which is a next step. Let us assume for the second equation, g is equal to 10, k is equal to 15, m is equal to 5. There are 10 equations. In total, 15 variables are there. And in particular equation, there are 5 variables. So k minus m, that is greater than or equal to g minus 1. The condition is satisfied and it is an exactly identified case, which is a desirable. The order condition for the identification is necessary for a relation to be identified, but it is not sufficient that it may fulfill in any particular equation and yet the relation may not be identified. Now, let us take this example. We are having this y1 is equal to 3y2 plus 2x1 plus x2 mu1. y2 is equal to y3 plus x3 plus mu2. y3 is equal to y1 minus y2 minus 2x3 plus mu3. How many endogenous variables are there? 1, 2, 3. How many exogenous variables are there? x1, x2, x3. Total number of variables are 6. 1, 2, 3, 4, 5, 6. Total number of endogenous variable or total number of equations are 1, 2, and 3. So g minus 1 is 2. Now let us talk about the first case. y1 is equal to 3y2 plus 2x1 plus x2 mu1. All these things are repeated till here. Now, what is a specific in case of equation 1 is we will have to count how many variables are included here. 1, 2, 3, 4. So, y1, y2, x1, x2. So, now I will use the equation k minus m greater than or equal to g minus 1. So, 6 total number of variables. M is 4. That is how many variables are there in a particular equation. Is equal to 3 minus 1. So 2 is equal to 2. It's an exactly identified case. Let us go back and try to understand the terminology now. It will be very clear that G is total number of equations, total number of endogenous variables. K is total number of the variables in the model, and M is number of variables in a particular equation. You can see here. Now, let's take the example of second equation. y2 is equal to y3 plus x3 mu 2. Till here, everything is repeated. M is 3. 1, 2, 3. So 6 minus 3 greater than 3 minus 1. It is an over-identified model, which is desirable. Let's talk about the third model, third equation. y1, y2, y3, x3. 4 are there. So k minus m greater than or equal to g minus 1. 6 minus 4 is equal to 3 minus 1. It is exactly identified model. So all the three equations can go for rank condition, but we will go for equation 2 as it is an over-identified. What are the implications of the identification of the state of the model? So if the equation is exactly identified, the appropriate method to be used for its estimation is a method of indirect least square. If the equation is over-identified, indirect least square cannot be applied because it will not yield the unique estimates of the structural parameter. So here we will be using two-stage least square method here. Or you can also use generalized method of moments or maximum likelihood methods. Next is rank condition. After establishing the order condition, we will have to go for the rank condition. In a system of G equation, any particular equation is identified if and only if it is possible to construct at least one non-zero determinant of order g minus 1 from the coefficients of the variables excluded from that particular equation but contained in the other equations of the model. This is a definition. When I will give you an example, you will be able to understand these things very nicely. Let's proceed further. Say, for example, if we repeat the same set of equations again, the first step is that you should bring all the variables on left hand side. You can see y1 is equal to 3y2 plus 2x1 plus x2 plus mu1. I've brought everything on left hand side. After this step 1 is over, you will have to write down first equation, second equation, third equation, and the variables which are there in all the equations. Then you will have to write down the coefficients of it. So let us see how we have written it. y1 is minus 1, y2 is 3, and y3 is 0. Let's confirm. Minus 1, 3, 0. Okay. Minus 2, 1, 0. Minus 2, 1, 0. Similarly, repeat the same procedure for second equation, third equation, second and third. We will be ignoring the random disturbance term in this table. Step 2. Eliminate the row of the coefficients of the equation which is being examined for the identification. Just try to recall, we will be using the second equation because it was an over-identified and therefore we want to test rank condition of it. Step 3. Eliminate the columns in which non-zero coefficients of the equations being examined appears. By deleting the relevant rows and columns, we are left out with the coefficients of the variables not included in the particular equation but contained in the other equations of the model. Let's see how we will be doing it. Step 2 and step 3. We are doing it at present. 1, 2, and 3 equations are there. This we had done in the previous steps. Now we want to establish the rank condition for the second equation. So first of all, we will delete second. So second equation is deleted. At the same time, y2 will be deleted from column also, row and column also. Now we will have to see which are the variables which are included in the second equation. So y3 and x3 are included and therefore we will have to delete that also. So y3 and x3. So you can see now we are left out with y1, x1 and x2. y1, x1 and x2. So minus 1, minus 2, 1, 1, 0, 0. How many determinants we can generate from this? So we can generate 3 determinants from it. y1, x1, x1, x2 and y1, x2. You can see here. From the determinant of the order g minus 1, we'll examine their values. If at least one of this determinant is non-zero, the equation is identified. If all the determinants of order g minus 1 are 0, the equation is under-identified. In the above example of exploration of the identifiability of the second structural equation, we have three determinants of order g minus 1. Let's see how. Minus 1, minus 2, 1 and 0. Minus 1, minus 2, 1 and 0. So 0 into minus 1, all those who are aware about how to solve the determinants. So 0 into minus 1 is 0, minus 2 into 1, so it is positive 2, and therefore it is not equal to 0. If I talk about second determinant, it is equal to 0 because minus 2 into 0 minus 1 into 0 is 0, and therefore it is equal to 0. If I talk about third determinant, minus 1 into 0 is 0, and minus 1, it is not equal to 0. So the condition is at least one of them should not be equal to 0. The symbol data stands for the determinant. We can see that from two non-zero determinants of the order g minus 1, that is 3 minus 1 is equal to 2, and the second equation of our system is identified. To see, that is at stage 5, to see whether the equation is exactly identified or over-identified, we use the order condition for second equation, k minus m greater than or g minus 1. This is the same step which we will repeat again. In the case of second equation, we have g is equal to 3, k is equal to 6, m is equal to 3, and the counting rule is k minus m should be greater than or equal to g minus 1, which gives k minus m is 3, and this is 2, and therefore a second equation of the model is over identified. Now consider the following model, that is rt is equal to beta 11 plus beta 2 mt plus beta 1 3 yt plus beta 4 mt minus 1 plus mu 1 t. Yt is equal to beta 2 1 plus beta 2 2 rt plus beta 2 3 it plus u1 t, where r denotes the interest rate, m denotes the money supply, y is GDP, and I is the investment expenditure. In this model, r and y are the endogenous variable. You can see here r and y are endogenous, and m and I are the exogenous variable. Equation 1 is exactly identified and equation 2 is over-identified. Now let us see how we can do two-stage least square in EViews. Now to conduct two-stage least square, we will have to go in the option of quick, estimate the equation, and we'll have to activate TSLS method, which is the second method, two-stage least square. Now we'll have to specify here that my y, c, r, I, and here I'll specify the instrument variable as c, m, I, m minus 1. It's the same thing which we have considered in our model, this one. Now I'll click OK. I got the results. I can run the same two-stage least square by the command line also, where I can write TSLS YCRI at the rate CMIM minus 1. I'll get the same result. You can see in my Word file the command line. Now how to interpret this output? Let's see. If you see carefully, the rate of interest is negative here. Moreover, it is significant. So the income and the rate of interest are negatively correlated. According to the theoretical prediction, an income is quite sensitive to the change in the rate of interest. Also, a change in investment would cause a function to shift to the right, again as theory suggests. One more thing to observe is that the R square is very high, and therefore the model is appropriate. Now the question arises, is Y and R the endogenous or endogenous variable or not. So for this, again, we will go in estimate and we'll make small changes here. We'll have to go from normal OLS. And here we will write R, C, M, Y, M minus 1, Y fit. Click OK. And you got the results. If you see carefully, Y fit term is significant. The conclusion is that the fitted value Y fit GDP is significant in R. So GDP can be considered the endogenous for rate of interest. As there are endogenous variables, normal OLS cannot be applied. If this was insignificant, if this term was insignificant, we could have very well applied the normal OLS. Now again, is R endogenous? So for this, again, I'll go in estimate, and this time I will change this to B. I'll make this as Y, C, R, R fit. R fit is already generated. You can see in the variable here, R fit, and I. Click OK. You got the results. This is less than 0.05. It is significant. The conclusion is that the fitted value term R fit, R rate of interest, is significant in Y GDP. So rate of interest can be considered endogenous for GDP. As there are no endogenous variables, as this endogenous variable is significant, normal OLS cannot be applied. If it was insignificant, we would have definitely gone for normal OLS. For more videos on econometrics, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter. Please don't forget to press the like button. Thank you.